Hi, everybody. We are on to section 11.4, and we're going to be talking about the cross product today. The cross product might ring a bell. We just talked about the dot product, and there will be some comparisons to draw between the two, but let's go ahead and look at the definition here. Given two non-parallel and non-zero vectors, u and v, the cross product is defined as a vector. So dot product was just a scalar, just a number. The result of the cross product is actually going to be a new vector. And what this will be is the magnitude of u times the magnitude of v times the sine of the angle in between them. And then all of that is functioning as kind of a weight on the normal vector to u and v that is perpendicular to both u and v at the same time, but is heading up according to the right-hand rule. And so if you want to get the direction of this normal vector down, yeah, you have your hand out like this. Your fingers kind of curled in the direction of u. Your arm is kind of, yeah, this is your right arm, of course. Yeah, your arm's kind of in the direction of v, and your thumb up will be the normal vector according to the right-hand rule. So yeah, like if we were going to take the cross product of I hat and j hat, pointing in the x direction, pointing in the y direction, what you would get would be k hat, the positive, z direction for their cross product. Notice though that would change if we change the order. We're going to look down here at the properties of a cross product pretty soon. And actually, when you change the order of the cross product, you end up reversing the direction, which is, yeah, kind of cool. We'll look at that soon. But yeah, I want to keep making a comparison to the dot product. So yeah, especially if we look at this part, this looks a lot like a dot product. And this is really more of the magnitude of u cross v. And I guess I could have written it like this. Boom. So yeah, that part's the magnitude, and it actually has a pretty nice geometric interpretation. So we're going to go to GeoGebra and check it out. All right, so I spoil it down here, but the area of this parallelogram in between two vectors, u and v, is actually the magnitude of their cross product. And one of the things that I've done here is I've left these blue I created these blue vectors very similar to what we have done with projections in 11.3, where this u1 is a projection of u onto v, so it's pointing in the same direction. And remember, the dot product was the length of this vector times the length of v. That was the dot product geometric interpretation. The cross product, however, focuses more on finding the area of this parallelogram. And in order to do that, instead of using the part of u, the component of u that's parallel to v, we use the component of u that's perpendicular to v. And because, if you think about, again, like v acting like the x-axis as in your normal frame of reference, and thinking about theta as an angle coming up from the x-axis, and thinking about u as maybe some point along the unit circle or something like that, the sine would be equivalent to the y value, the cosine would be down to the x value. So what this quantity is, the length of this vector is the magnitude of u times the sine of theta. So that's where that's coming from. And in order to get the area of the entire parallelogram, you have the magnitude of V times the magnitude of U times the cosine or the sine of the angle in between them. So yeah, calculating the area of parallelogram, we need base times height, and the height needs to be perpendicular to the base. And yeah, the length of the cross product vector that we create using the right-hand rule is the same as the area that we have here. So that's cool. If you have any questions, go ahead and pause and see if you can figure things out. But yeah, that's the definition of cross product. And let's take a look at some of the properties. Again, so we have this property that when we reverse the order of vectors that we are taking the cross product of, we get a vector in the opposite direction. And sometimes this is called anti-commutative. So a big word, but that's cool. So we've got this anti-commutativity property. We have a lot of different like flavors of the distributive property. This part is the distributive property with respect to vector addition. This one just shows that scalars behave well. The next one is what happens when you take the cross product and then take the cross product again. This is a little bit, crazier. Honestly, what I would do is probably just take the cross product between V and W and then do the cross product again. But this is a nice shortcut. As we will see later, there's actually kind of a cool connection between the cross product and dot product together. When you combine them, you actually get something called the triple scalar product, and it really just behaves like the determinant of a matrix, a 3x3 matrix. But yeah, we'll see that soon. This one, I don't know if we're going to use that much, but it's there. Taking the cross product between the zero vector and any vector is going to be zero, because the zero vector is not really pointing in any direction. It's just there. So there's not really much to go off of. Here we've got the distributive property again over vector addition. It's just that this time the vector addition comes first. So, okay, great. And then this one is associative property of the cross product associated with the dot product. This one's actually that triple scalar product that I was talking about. Triple scalar. This one's for finding volumes of parallelepiped. Yeah, that we'll see soon. And honestly, you can just do that with a 3x3 matrix. They're equivalent. Okay, so there's some properties of the cross product. Cool. Moving on, I'm going to motivate this other formulation of the cross product, because like the dot product, there's this way of formulating the cross product where we know some magnitudes and we know the angle in between two vectors, and we're able to, calculate a cross product based on that. But, just like the dot product has kind of the taking the product of components and then adding them together, the cross product is going to have a formula based on the components of the vectors. It's a little bit more complicated than the dot product, but we're going to get there. It's all based on determinants. And if you haven't dealt with matrices before, you've probably never heard of a determinant. But what I have here is a little diagram showing you that if we start off with two vectors, we've got AC here, where A is equal to 4 and C is equal to 1. I do have a GeoGebra thing of this where we can drag it around if we want to. But we've got one vector that's 4, 1. We've got another vector that's 2, 3. And I'm labeling these components A, B, C, and D because this is typically what ends up going in as entries of a matrix that we then take the determinant of. So this is one notation for a determinant. Just writing DET outside of the matrix tells you to take the determinant. Also putting the vertical bars on the outside of a matrix tells you take the determinant. And really, in a 2x2 matrix, taking the determinant is really easy. All you do is take the product of the main diagonal elements, so A times D, and then you subtract the product of the off diagonal elements, B times C. So in the end, we get A times D minus B times C, which is, it's kind of similar to the dot product in that we're, multiplying things and then in this case, subtracting them. But yeah, that's the short form. And the reason why this always works is kind of illustrated here on the picture. If we look at the area of this big rectangle, notice that the side would be A plus B, this side would be C plus D. And so the area would be length times width, A plus B times C plus D. So that's the big rectangle. And then to get the area of the blue parallelogram, what we would need to do is subtract off these orange triangles, which if you put those triangles together, they become a rectangle. And the rectangle has dimensions A and C. So minus AC for the area of the orange rectangle. Similarly, minus BD for the area of this pink rectangle. And then minus 2BC, because we actually have two rectangles here and here that have dimensions BC. And when you use the distributive property and multiply these out, some cancellation happens with the minus things that we have over here. And eventually you get the same thing as this quick, convenient way of calculating the determinant. AD minus BC is still a valid way to find the area of this parallelogram. And that works even when you shift things around a little bit. The determinant does get a little bit more complicated than just finding area because it actually determines signed area. Right now, the red vector is in a certain orientation with the blue vector. And if the orientations were flip-flopped so that, one was clockwise or counterclockwise of the other one, flipped from where they started, then area gets counted as negative area in that case. And that's, a little bit weird, but we will definitely delve more into the properties and details of determinants when we get into linear algebra in the spring. But for right now, what I want you to get is that these things called determinants can be helpful for finding the area of parallelograms. And what is this thing? Well, the cross product, the magnitude of the cross product is actually the area of a parallelogram spanned by U and V. Okay. So Yeah, I don't know, draw a parallelogram down here. Woo, okay, excellent. Cool. So now let's look at the actual cross product formula. This is actually a 3x3 determinant. Notice that we have those vertical bars. And this is weird. Normally when we're taking the determinant of matrices, all of the entries of the matrix are just numbers, just normal numbers like you'd think of. But notice in this cross product formula, that we have some numbers down here, U1, U2, U3, those are just the components of U, same one for V, but I, J, and K here are each vectors. This is I hat in the X direction, the unit vector in the X direction, unit vector in the Y direction, unit vector in the Z direction. So we have a matrix that has dissimilar things thrown into it. And it's a little bit weird notation coming from a mathematician's perspective, but there's actually some beautiful kind of geometry behind it that we will explore in more detail again in linear algebra when we have the vocabulary to talk about linear transformations and all that kind of stuff. There is a video down at the end of this that goes a little bit more into cross products if you're interested, again on the 3 Blue 1 Brown channel. But yeah, for right now, what we need to think about is just the mechanics. How to take the 3x3 determinant. We're gonna focus on I for the first one. So for this one, we're going to keep I, and then the 2x2 matrix that goes along with I is the submatrix where you ignore the row and the column associated with I. So that's the first 2x2 matrix that we get, and then taking the determinant of that 2x2 matrix just happens to come down here. So very similarly with J and K, do notice that there is a minus sign here. The signs do alternate, so positive, negative, positive. And that kind of a pattern would continue if we were taking a larger determinant of a 4x4 or a 5x5 matrix, but we're really focused on this specific determinant that defines the cross product. So just remember that there's a minus sign associated with the J. And that happens, I don't know, that is because we're doing a cofactor expansion, and that's linear algebra stuff. But if we wanted to look at J, the submatrix that we would be working with, again, would ignore the row that J is in and the column that J is in. And that would be the submatrix that ends up here. And very similar story for K. K would be the leftmost submatrix. So yeah, this can function a lot like just an algorithm that you do this. You take your two vectors, plug them in, take some determinants, and then these will just be numbers that pop out. And in the end, the result is actually a vector, because really this 2x2 determinant determines the weight on I hat, meaning that this gives us the X component of our vector, this is the Y component of our vector, and this is the Z component of our vector. So this is just like an expanded form of writing one vector down. Yeah, and there's a proof of this cross product determinant formula, because again, they do encourage just looking at this as a convenient reminder of the formula, but there's a lot going on here, so I wrote some notes to the side. If we look at write U as this expansion with the components of U and this expansion with the components of V for V, U cross V looks like this. We've got U, we've got V, and then we start using the properties of cross products. Here we're using the distributive property, where we're using the distributive property of the cross products over vector addition. So these blue components are coming out here, all associated with the V vector. Well, yeah, the V vector. And yeah, in this next step, we're factoring out some scalars. And this is where we start. But we're also, I mean, we're doing the distributive property here too. We get some cross products between the standard basis vectors amongst themselves. So here's where we do calculations like I cross J equals K, or I cross K actually ends up equaling negative J. And I included a little chart over here. Make that a little easier to read. This gives you a summary of the results. So this is where we start. If we do I cross J, the result's K. And we have this anti-symmetric kind of nature to this chart, where if you've got K on one side of the diagonal, you've got negative K on the other side. Yeah. And that's not necessarily, you know, these operations are not something that you have to memorize. Cross products are definitely something that calculators can, you know, help with. What we're doing now is just trying to understand the concepts. Yeah, so here we're performing cross products, and all the terms that have I cross I or J cross J, all of those go to 0, just leave. And then eventually, you know, we collect the coefficients corresponding to what's left with I hat, or what's left with J hat, or what's left with K hat. And we get the same 2x2 determinants that we had above here. And yeah, there is some nice geometry that we will talk about in linear algebra regarding that. Maybe this would be a good time to pause and try out any of these that you want to do. Try to simplify these 4 cross products using the properties that, you know, we mentioned above. And I'll try to do them and we can compare answers. All right. I cross K. That's negative J. I cross negative K, I think would just be J. I cross J plus I cross K, distributive property. I cross J is K, and I cross K is negative J. So this one ends up being the vector 0, negative 1, 1. And then this one, I mean, we could pull these numbers out, so we could have a negative 6 and then times I cross K. I cross K again is negative J. 6 times negative J. And so we just get 6J here. So that's the vector 0, 6, 0. So yeah, I don't know. If I got those wrong, let me know. Hopefully I didn't. We can check real quick. There we go. Oh, geez. Negative j, then j, 0, 1, 1, and yeah, 6j at the end. Great. Simplify, yeah. Oh, yeah. Look at that. Oh, that's interesting. They just took the cross product without using the properties. They actually added j and k together before doing the cross product. Properties made it easier. Okay. Back to this. Example number 2. This is just a straightforward calculation of the dot product. This is really just kind of going through the motions of doing the multiplications. If you have any questions about that, again, feel free to pause and just make sure you kind of understand what's going on. And if you all do, feel free to keep going. The next thing I want to motivate is that everything is a plane if you look hard enough. And we have Rafiki here to remind us to look harder. What I mean is, we are actually in multivariable calculus, even though we haven't done any calculus yet. Eventually, we're going to want to take some derivatives. We're going to do integrals. And in the context of derivatives, in single variable calculus, we were concerned with finding tangent lines, right? In multivariable calculus, we're going to be searching for tangent planes. And I guess this is just motivating that planes are important in general, but and I guess maybe this is motivating linear algebra, the context where we really do study planes and linear subspaces in detail. But yeah, I've got this really curvy surface, and if we do zoom in towards the point A, this far zooming still looks pretty curvy. But if we continue, zoom and enhance. All right. That's still kind of curvy. Go. All right, we're zooming in even farther. Yeah, that's looking to be pretty planey. So yeah, one of the things that we will use in calculus is the fact that any differentiable surface is going to look like a plane if you zoom in far enough. So finding tangent planes to surfaces is going to be a thing. And actually what we're going to do is we're going to calculate gradients. A gradient is going to be a normal vector to the surface. So yeah, that black line, it's actually a vector pointing in a direction that is orthogonal to the surface. And creating a tangent plane is really just creating a plane that based off of that orthogonal vector, which we're going to look at really, really soon. So yeah, now we're zooming back out. Look at that, that's nice. And yeah, as things change, the gradient changes and the tangent plane changes. And we're going to have fun with planes and normal vectors. That's why we're doing this stuff, so that we can use them with calculus eventually. Okay, back to OneNote. Example number 3. We are going to construct a normal vector to the plane containing these 3 points. And I think what I want to do is probably just use GeoGebra to guide us through this. So we've got 3 points here. And I'll just guide you through the steps on GeoGebra because that's, I mean, we're in a video. Boom. So we have 3 points. P is -2, 1, 3. Q is 4, -3, 1. And R is 5, 5, 3. So they're all hanging up here above the XY plane. And our goal is to construct a normal vector to the plane that these 3 points occupy. And in order to construct a normal vector, well, maybe we could use the cross product. And in order to use a cross product, we need a couple vectors to take the cross product of. So in order to create the vectors that we will take the cross product of, we can define U as R minus P, boom, and V as Q minus P, so that they both start at P and end at R and end at Q respectively. So P is kind of our anchor point here. Now what we would do is, since we have these two vectors, 7, 4, 0 and 6, -4, -2, we can take the cross product of those. And if you want to see that done out by hand, you can do that with Allie. For right now, I'm just going to let this do the cross product because it is 12:15 and calculus will soon be upon us in real life. So yeah, there's a cross product. And notice that the cross product is normal to the plane here. So I can use GeoGebra. GeoGebra has a function for defining a plane through the 3 points. But what's more interesting, and it's actually what we're going to be studying in section 11.5, is based on this normal vector, which happens to be at -8, 14, -52, how can we use the normal vector to actually construct the plane? And one thing you might notice is that 4, -7, and 26 are all multiples, or a factor away, a common factor away from these coefficients. And indeed, we use the normal vector to define a plane. Hopefully I show this to you. Well, actually today will be, no, I'll show it to you tomorrow for a homework day. Hopefully we've discussed that planes are the solutions to dot product equations. And if we haven't yet, we need to do that soon. But yeah, if you take the dot product of an arbitrary vector, x, y, z, and you dot product that with the normal vector that we have here, and set that equal to 0 or just any number, you're going to get a plane. So if I were to set that dot product equal to 0, now that's -5. Good grief, here we go. Oh. Oof. All right, we're going to set this equal to 0 so that we see what happens. But yeah, when you set that dot product equal to 0, you get a plane that's going through the origin. But what the constant on the right-hand side of this plane equation does is shift the plane along the normal vector, and it encapsulates all of the different points that would have a certain dot product with the vector -8, 14, -52. So all of the vectors on this plane would have a dot product of -88 with the vector -8, 14, -52. And eventually, once we move this number on the right-hand side of our plane equation enough, we do get the actual plane. This one's just close. This is the actual plane. But yeah, that's something that we'll talk about in 11.5. So cool, we constructed that normal vector the normal vector was this W, the cross product of U and V. Cool. Continuing on. Example number 4. These two vectors are used to construct a parallelogram shown in this figure. Find its area. Since we've already talked about taking a 2x2 determinant, this example's kind of trivial. To find the area of this, what we can do is, treat these as column vectors and put them in as entries of a matrix, and then take the determinant of said matrix, so that we would have 6 minus -4, or would be 6 plus 4, and the area is 10 here. And do know that we would have the option of calculating the area here using the magnitude of the cross product, and we could pretty easily extend these vectors to be their 3-dimensional counterparts that would just be lying in the XY plane. So you could add a 0 to the end of these vectors and take the cross product that way. Or you could just think about it as the magnitude of U times the magnitude of V times the sine of the angle in between them. And that would give you the area of that parallelogram as well. But yeah, the easiest way, I thought, 2x2 determinant. Yeah, so there's 3 different ways there that you could find the parallelogram. Determinant, making these into 3-dimensional vectors and calculating the cross product like we've been normally doing, and then using this formulation of the magnitude of the cross product as well. Example 5, I left the solution here because it's kind of boring. Once we've been calculating areas of parallelograms, the area of a triangle's not too big of a deal. All you do is take half of the area. So calculate the cross product for these two vectors, and then divide the magnitude of that cross product by 1/2, and you get the area of the triangle. This next part's pretty cool. Here we have the parallelepiped that we hinted about earlier with the triple scalar product. We've got U, V, and W that make this parallelepiped, like a 3-dimensional version of a parallelogram. And the idea here is that the volume of a parallelepiped is determined by the cross-sectional area times the height. So we would be finding the area of the parallelogram between U and V, and then we would just need to figure out a height that is perpendicular to that, for this parallelogram. And the idea for the height is that it's not going to be the magnitude of W exactly, because W can be slanted. But what we would want to do is project W onto the cross product of U and V, because we know the cross product is perpendicular to U and V. So that gives us a really nice direction for the height. And so, how this works out is the area of the parallelogram gets covered by the magnitude of U cross V, and then the height gets covered by W times the cosine of theta, where theta is measured between W and the cross product. And you get this cool thing called the triple scalar product. And I don't know, we could work through the details of that and mess around to maybe see how we get here eventually. But the result that you get of this triple scalar product is really just the 3x3 determinant of a matrix. And this matrix is nice and well behaved and actually has just numbers as entries. So literally all you've done is put the coordinates of the 3 vectors in there, and you're good to go. You take a 3x3 determinant and you can find the volume of a parallelepiped. In linear algebra, these kind of determinants are going to be really useful for determining how space gets stretched and squished, and the scale factor by which that stretching and squishing happens. So that's, yeah, for this class, we're not going to be finding the volume of lots of parallelepipeds. That's just a cool application of the cross product. And here's one of them worked out. Example 6, we have U, V, and W. We put those in as rows of a matrix. We compute the 3x3 determinant, and we get -3. What that would mean in a linear algebra sense is that somehow three-dimensional space has gotten stretched in such a fashion that the standard basis vectors have changed their orientation, so that if they started off at a right-hand rule, they would kind of be forming a left-hand rule after the transformation. That's why we had this negative sign there. But yeah, the volume would be scaled by a factor of 3 from where it started. Anyways, probably an application that will be interesting to more of you, especially like mechanical engineers, is torque. Torque can be measured as, the magnitude of the length of a lever arm times the force that's being applied times the sine of the angle in between the direction of the lever arm and the direction of the force, so that we can capture torque as a cross product. And yeah, if you want to think about it as like tightening a bolt creates a torque vector tau that drives the bolt into an object. So you're actually getting some perpendicular motion to the way that you're rotating. And likewise, loosening and turning the wrench counterclockwise backs the bolt out of the object. So we get that kind of like, we're working in the plane of U and V, but the action that's happening to the bolt is perpendicular to that. So that's cool. And this is what that math looks like. We've got a 1-foot wrench. We have a force of 20 pounds being applied in a direction that's 75 degrees. Kind of seems to me that you'd be aiming for 90 to apply maximum torque. And so that you don't accidentally pull the wrench off of the bolt head. But yeah, all of this is, it's really just the 20-pound force times the sine of 75, because you're not getting all of that force because not all of it is being directly applied to kind of the perpendicular direction. But yeah, it's almost 20 is what it works out to be, 20, about 20 foot-pounds of torque. So that one's a cool kind of like application where you might see this later in life. Again, there's a video on cross products that's on 3 Blue 1 Brown. If you're interested in learning more, we will discuss this more in linear algebra though. And yeah, if there's still some time in class and you guys want to work together on something, number 66 is assigned for written homework. This one might take a little bit of ingenuity. We really are going to make finding the equation of a plane a focus of 11.5. But without that stuff, you'll need to get a little bit creative. Do know that you're going to be aiming for finding a normal vector to the plane that those points lie in. And then the tricky part will be finding, out the constant part of the plane, because you'll just be able to use the components of the normal vector on the left-hand side of the equation with x, y, and z. But the right-hand side, you'll have to figure that out. It's kind of similar to back in the day when you were finding the equation of a line and you had this y equals mx plus b, you had found the slope, but you still needed to find the y-intercept. So you're still kind of solving for that b. That's what you're doing here to make sure that the plane ends up lining up with all of the points. So using one of those points to make sure that the equation works out will be a good way to go. All right. Hope you guys have a good day, and I'll see you next time. Bye.